Welcome to the ML Platform Podcast, brought to you by Neptune AI. In a show where Piotr and Arimas, together with top MLOps practitioners, explore the world of internal ML platforms and MLOps stack components. Today, we've brought Frank Liu from Zilliz to talk about navigating the vector database landscape, including indexing strategies, GPU, and real-world use cases.
At about 1 million vectors, that's when you grow from just using vector search library into using a proper vector database. A lot of the magic of vector search really comes from what index to use, how to build those indexes, and why should I select one index over another? Because what am I doing with vector search? I'm essentially doing lots and lots of math, tons of math. But if I do a pre-filter, I just need to do a comparison.
Now onto the show.
Hello everyone and welcome to Machine Learning Platform Podcast. Today with me, as always, I have my co-host Piotr Nedvich, who is founder and CEO at Neptune AI. And as a guest, we have Frank Liu, who is a head of AI and ML at Zilliz. And I do believe that this will be a super neat episode because we will be covering vector databases. Hi, Frank. Can you tell us something to our listeners about yourself?
Yeah, sure. Hey, Arimas, and my name is Frank. First of all, thanks for having me on the show. It's quite an honor. And, I've been in and around AI ML probably for the better part of 8, 9, coming up on 10 years now. So been around here for a while, ever since the early computer vision AlexNet days, backwards features. And I actually started my career at Yahoo. Afterwards I did a startup for a period of time. And then in about 2021, I got approached by Zilliz, and really the mission that Zilliz was undertaking back then really resonated with me, right? The concept that, hey, vector search is going to be a core part, not just of AI/ML, but really for any type of unstructured data. I felt like that was a really, really compelling argument, and I felt really attracted by the thesis of Zilliz as a whole. So fast forward today, I work with a lot of our users, some of our prospects, some of our customers, and I do quite a bit of machine learning here at Zilliz as well.
And guys, I think that it would be beneficial for folks listening to our podcast. It would be definitely something that I would like to know. Year ago, now I've I've catch up what vector databases are about. But in general, we have a lot of databases, right? Like potential storage options. What is so special about vector databases? Why do we need, additional type of database, and what we can get from it? What are the main use cases for vector database in general?
Yeah, great question. I'm going to talk about vector databases from two different perspectives. One is more from an old school perspective. So from before ChatGPT, before large language models, before autoregressive models. And I'm going to sort of talk about it a bit more from a new school perspective as well, from a modern perspective, quote unquote. And it feels very, very strange to say this because vector search has actually been around for a long, long time, right? If you talk about a lot of the if you talk about, for example, SIP features and you talk about descriptor matching, all of that is pretty much vector search, originally using KD trees and other data structures. But vector search, as it relates to deep neural networks, as it relates to deep learning, I would say it really hasn't been around for that long. It's been around for probably about a decade, and starting off with, well, I take that back. It's been popular for about a decade. Starting off with when folks discovered that you could really, these embeddings from deep neural networks, from trained convolutional neural networks, were very representative of your input image or of your input video or audio snippet or, any other type of unstructured data that's out there. So early on, vector search and vector databases were used primarily for things like recommendation. So you can imagine if I have, if I'm, a big e-commerce website, I have all these products or pictures of products, and I have a purchase history. Maybe I want to find similar products to those, not just by, hey, who's selling the product, or not just by the title of the product or the description of the product, but also by pictures, videos of that product as well. It's one of the ways that we can do recommendations with semantic matching, semantic recommendation. There's also other things like fraud detection that vector databases were used for. There's AI drug discovery and a wide range of other retrieval and search applications as well. It's really traditional. That's what vector databases in traditional sense, in more of an old school sense, right?
And Frank, so based on this description, like I assume that it is like looking at the just raw API, like bare primitives behind it. We have a vector, and we want to find, and in the database we have a lot of other vectors, and we want to find a similar vector, right?
Yep.
Like whatever it means, based on some distance metric.
That's right. Yep.
What about would it be something that you would also use for anomaly detection to maybe find, to figure out, okay, actually yeah, you will find the closest and it is far, then maybe it's
Absolutely.
anomaly.
Absolutely. Yeah, for anomaly detection. And for anomaly detection, fraud detection, or anything along those lines. And I'll sort of explain. I think it's probably a little bit prudent of me to take a quick step back and explain how vector databases and how these embeddings work in general, right? And I don't want to limit it necessarily to trained neural networks, but I'll use trained neural networks as really the backbone here. And if I have any type of if I have any type of neural network, it could be, one of the more modern transformer models, it could be an old convnet, and I look at these, typically one of the latter layers or one of the outputs of the later layers. The result of that is typically, is a high dimensional tensor known as an embedding. And long story short, and I won't dive too deep into it, but the more similar or the more relevant, more semantically related that your input data is, the closer these embeddings are going to be to each other. I use this example all the time. I've been using this example for like a year and a half at this point, where if I have two pictures of German Shepherds, my favorite kind of dog, these pictures, they could be with different backgrounds, they could be, doing different things, but with a neural network that's trained to classify, let's say, different breeds of dogs, these embeddings would be very, very close to each other after I run these two images through my trained machine learning model. And the reason is because that model has been trained to pick out the specific breed of the dog, right, in your input image, and really ignore a lot of the other auxiliary information.
If we are talking about object classification.
Exactly. Classification or detection to a certain extent as well, right? And again, I'm simplifying things significantly, but that's the general idea, is that you have these high dimensional tensors, which are extremely representative of your input data, and it extends to beyond images as well, right? It extends to natural language, it extends to audio, to video, any type of human generated data. There's a recent paper from Meta called ImageMind, and they actually embed IMU data into the same space as image data as well, which is really, really quite fascinating. I recommend all the listeners go take a look at that ImageMind from Meta. And that's the core principle. This is the idea that embeddings, which are closer to each other, means that the data is more relevant in some way, shape, or form, depending on how your model is trained. That's the core principle that vector databases use. That's the core principle that vector databases leverage, right? And really what vector databases are meant to do is they're meant to store, index, and search across these vast quantities of human-generated data or unstructured data using their embedding representations. So you can imagine this way, right? So if I have, going back to your example, Peter, about anomaly detection or fraud detection, if I'm a big bank and I have all these transactions, right? I have tons and tons and tons of transactions. One of the interesting use cases that I can use a vector database for is I can actually turn those transactions, details about those transactions, into an embedding, right? Into an embedding, and I can search in my vector database for nearest neighbors. And if most of those nearest neighbors correspond to, or let's say 98 or 99+% of those nearest neighbors, if they correspond to valid transactions, non-fraudulent transactions, then I know that my transaction, this new transaction, is probably also non-fraudulent. I'm pretty confident, right? I'm very, very confident. But if any of these nearest neighbors, if I have, let's say, greater than 5 or 10% of my nearest neighbors are fraudulent, then I probably should run this particular transaction through a larger machine learning model, one that is one that is trained specifically to do fraud detection to figure out whether or not this is truly fraud. So you can think about how vector databases work from not just the perspective of images, video, audio, text, but really for any type of data that you can't put into, let's say, MongoDB, or any type of data that you can't put into a wide columns tool or in a relational database, right? The paradigm is always the same, is that you take the embedding representation and you search for nearest neighbors.
Okay, it's not necessarily must have to know for end users how it works, what is the time complexity under the hood. But because of my algorithmic background, it is a topic that's sparked my attention. How does it work? Is it a brute force? You go through all vectors, but it is just distributed and then collect, or there is some magic inside?
Typically so in Milvus, in the open source vector database that we've built, you do have an option to do brute force search, but I never recommend that for anybody that I talk to, and I never recommend that for any of our users. And the reason is because it's not scalable, right? You end up taking, if you have a very small data set, if you have like 10,000 vectors or 100, maybe even 100,000 vectors, I would say go for it. Do brute force search. You'll get perfect recall all the time, and you pretty much have it simplifies your deployment significantly.
And Frank, one more data point, if you can share. What would be a typical length of a vector? Because we are talking about higher, like we are talking about the last layer of the network. So I expect it wouldn't be so huge, but you know the statistics better here.
So I've seen as low as 96 dimensions, and 96 dimensions is considered very like 64 and 96 dimensions is considered very, very small. There's not much information that you can encode into that space, and I've seen it go all the way up to over 10,000. But the typical range I would see is something like maybe between 512 and 1536.
But at least they fit in a memory, in a RAM memory, like a vector. It's
definitely it's 512. It's 512. So if we're to do the math here, let's say we have 768 length vectors, so it would just be 768 times 4. Or 768 times 2 if you're using bflow16 or some other, or flow16, right? Would be the number of bytes that it takes up in memory, and that each vector takes up in memory, excuse me. Now, if you're talking about a vector database, right, typically you'd want billion scale, or maybe you'd want 100 million scale. You want the capability to store tons and tons of vectors, my entire data set of vectors, and the capability to search across that very, very quickly and very, very rapidly. Right? That's what a vector database affords you. And once you sort of going back to your original point, Peter, is once you reach 100 million scale and once you reach billion scale, it's like good luck doing brute force, right? It's not scalable. Linear time when it comes to nearest neighbor search it's not ideal.
But at least it distributes well, right? Like, but it would be costly depending on the amount of requests you would have. But
yeah, you could make it distributed, and if you really wanted to have perfect search, you could just do brute force distributed. But even so, you imagine I go back to the example of a billion vectors. I distribute that across 10 machines, still 100 million vectors per machine. That's still going to take me a long time for a single query.
But realistically, like I'm really, how often would you have such a big amount of vector? Because I expect that a vector, like let's say transactions, right, would represent a transaction. When we are talking about computer vision, a vector would represent a picture. So typically, I you know better, right? But I won't expect to have a billion.
Yeah, unless you're a mid-market company, or unless you're, a publicly traded company or a Fortune 500, you probably won't have a billion, most likely. If you're Fortune 500, you probably would have a lot more than that. But still, if we do flat indexing, it's still not ideal, even once we get to the million scale level as well, right? If we just want to do brute force. Now I will be very, 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 I will be very honest. There are ways to, well, okay. Well, before I get there, I'll go through the rest of my spiel first. So there's brute force search and there's flat indexing. Yes, while we can do it in a distributed way, it's still not ideal, because oftentimes you can imagine if I'm building an application on top of a vector database, I want to be able to have high throughput. All right, I want to be able to, let's say, have 100, maybe even 1,000 queries per second. I want to be able to have low latency as well. If I do flat indexing or brute force search, my indexing speeds just, they fall off a cliff. All right. And the trick to all of this is to use an index, a vector index, and move away from exact nearest neighbor search into what's called approximate nearest neighbor search.
Do you use some k-means algorithm under the hood to just have a representative sample of vectors? How does it work?
Actually, yeah. So that's one of the strategies that you can use. That strategy is called IVF. So building an inverted file. And what you do is, you run k-means over your input or your training data set. And what that do is I'll give you centroids. Now, when you have a new query vector come in, you first compare your query vector to all of the centroids in the data set. You find the nearest centroids. You find your nearest centroids. The value is typically called nprobe, and you will dive deeper into the centroids and then do the query across all of those as well. So yeah, exactly. So that's one of the strategies that you can use to speed things up, is to build an inverted file. And with inverted file, not only can you do approximate nearest neighbor search, right? But you can also there's ways using the triangle inequality to do exact nearest neighbor search with inverted files as well. I won't go too deep into that, right? It's a little bit more math heavy. But the idea is this, right? We can make vector search much, much faster. So rather, if I have like a million data set, a million vectors, instead of taking 10 seconds to run a query, I can make it run in milliseconds, just like that, right? But there's no free lunch. If you listen to your economics professor in college, or whoever, there's never a free lunch.
So we need to go to your pricing.
Go to our pricing. Yeah, go to our Zillow Cloud website. Look at our pricing. But yeah. So at the cost of this huge speed up, I lose a little bit of recall. I lose a little bit of accuracy. Basically, instead of my exact, I retrieve, again, a vector database is all about retrieving nearest vectors, nearest neighbors, and instead of retrieving those exact, let's say, top 10 or top 20, top 100 nearest neighbors, maybe only 90% of them are real nearest neighbors, are real top 100 nearest neighbors, right? So I have 90% recall. Maybe I have 95% recall, depending on the algorithm that I use. So it's not perfect. We no longer have perfect accuracy, but oftentimes that's a very, very small price to pay relative to the gains that we get in QPS, the gains that we get in throughput, the decreases that we get in latency as well, right? We're able to conduct vector similarity search much, much more efficiently with approximate nearest neighbor search, with this type of vector index. So, you mentioned using k-means to do some clustering, and then, potentially do some quantization on top of that as well. Yeah. So that's typically something known as IVF, or potentially IVF-SQ, IVF-PQ. All of these are available in Milvus, in our open source vector database, as an indexing strategy. But I would say the most commonly used strategy today is something called HNSW, hierarchical navigable small worlds. And again, I won't go too much into it, but you're essentially building these different layers of graphs. So vectors which are near to each other are going to be more connected to each other. And the different layers are, they have longer connections at the upper layers and shorter connections at the lower layers. So you essentially traverse the first layer first, and then you traverse the second layer, traverse the third layer, traverse the fourth layer, and that gives you a very, very efficient way to conduct vector similarity search. So instead of linear time, you get logarithmic complexity. Can't talk this morning. But yeah, and there's tree-based strategies to do approximate significant search as well. There's also hashing strategies, LSH and so on and so forth. But again, the concept is the same. Is you want to conduct this vector similarity search, but you want to do it fast, and you want to do it. You're willing to sacrifice a little bit of recall to do it fast. And that's what vector databases are all about. And that's where a lot of the secret sauce when it comes to performance, it's one of the reasons why Milvus is incredibly performant, is because we do have some really unique ways, not just of optimizing the indexing strategies and the querying strategies, but using state-of-the-art indexes as well.
Yeah, what about writes? It sounds like these are very relatively complex indexes that you're creating. What about writes? Do you have any numbers of how much the write throughput kind of suffers? Can you update vectors in place? What are the
vector database that we've built is actually index agnostic. So what I mean by that is, irrespective of what index you use, the distributed portion or the database portion itself is exactly, it remains exactly the same. And we do that using the traditional database concept of segments, right? So we'll actually segment the data, and once your segment reaches a certain size, we will seal that. So instead of creating one huge index, right? Instead of creating, I have a billion vectors, and this billion vectors is all crammed into one index, I actually create many, many small indexes. And that is what that gives me, is it fixes a lot of the underlying problems that you get with embeddings. And again, it's like a lot of detail here. I won't go too deep into it. One of the examples is domain shift. So going back to the example of German Shepherds of images, if in 2023, I'm indexing a lot of German Shepherd photos, and then in 2024, I index a lot of Golden Retriever photos. That's the domain of my data has shifted, right? And with segments, you sort of solve that to a certain extent. But the other thing about segments is that it enables you to build a distributed vector database, right? So if you want, you can have certain segments assigned to certain query nodes, to certain machines, and those machines will be responsible for a subset of the data, and you combine all of that. You combine the results of each of those individual machines later on.
And how and if it's not too complicated, what determines to which segment particular vector would be assigned?
Oh, it's just by time. Yeah. So as new vectors come in, these segments will grow, and they reach, let's say, 512 megabytes or 256 megabytes, some fixed number of vectors, and that segment will become sealed in Milvus, right? And once you have a sealed segment, that segment is then, that segment that gets sent to an index node, and your index node will build the index across that segment. Once that index is built, it'll get sent over to the query node, or one of the query nodes, and the query nodes will then use that built index to do the query.
And what does it take to combine, because my assumption is that when you're then doing a search query, you need to somehow use those segments, like all of them, right? Or not?
Yeah, you would need to use all of them, right? Otherwise, you're essentially missing part of your database. And the typical process for this is you have multiple query nodes, and you could have multiple segments assigned to those query nodes. So, again, if my segment size is 512 megabytes, but my query nodes have 4 gigabytes of RAM each, I can assign multiple segments. I can assign 8 segments to those comfortably, right? Or again, I won't go too much into details, but that's approximately how that works. And yeah. Now that's how it works in Milvus, right? So for other vector databases, for some other vector search libraries, they do just build one index across your entire database. And that minimizes the flexibility that you have to build a distributed database, simply because how are you going to divide up that index, right? We don't know. We need to know beforehand, not just what index we're using, but also the structure of the index as well. It makes things much, much harder.
Yeah, I was thinking that maybe if you had okay, I thought initially that it is segmented by centroids, but I assume that there is some process of resegmentation, like after you increase data by this percentage or so.
And the index itself lives in a single node, right? The query node.
Yeah. So one segment will live in a query node, and there's one index per segment, right? So you have the same number of indexes as you have segments.
How then do you combine the index itself together, right? Because it has to eventually contain all of the data, not all of the data, but all of the pointers to the data, because you want to do ANN through all of it. I think that's also what was Piotr's question, right? If it's distributed, how do you make sure that you kind of search for exactly what you're searching for, right?
What you do is you'll have all these segments, and you'll have segments are assigned to query nodes, and you'll have multiple query nodes as well. So if I have 4 query nodes, each query node has 4 gigabytes of memory, and each segment is 512 megabytes, for example. Again, I'm sort of simplifying things here. I can have a total of 16 segments, right? And those 16 segments will be spread across my 4 query nodes, and I will use each query node will be responsible for searching across all of those segments, right? And figuring out, okay, figuring out for each segment, what are the nearest neighbors, right? So if I have a top 10, I'll find a top 10 for each segment. And then, right, I have another very, very tiny, very, very fast operation, which will go and fetch the top, let's say the top 10 out of the true top 10 out of those top 10 for each segment.
Kind of map reduce.
Exactly. Yeah, exactly. Like map reduce.
So you're increasing total computation needed, but still return completely accurate results, right?
What's amazing about using segments is that you effectively get higher, a little bit, you do have a bit of penalty in terms of performance, but you effectively get higher recall as well, because you've essentially done, in a way, instead of just a pure top 10 across one big index, you have many, many small indexes. You do a top 10 for each small index, and then you combine the results afterward. So you effectively get a little bit higher recall, right? Again, depending on the index type they use and depending on how those indexes are constructed.
So one of the big probably challenges in kind of using vector databases in machine learning applications is updating embeddings, right? So you change a model, you need to basically update the entire index. Is there any breakthroughs of being able to maybe do that in place and maybe creating a new version of already existing index in place and just commit it at some point in time so that you don't need to create a new one?
That's always a tough question. We actually get this question a lot. Now, typically, if you use a vector database, you'll have an embedding model that you want to use in mind. And that embedding model hopefully won't change for a period of time. If you do get a V2 or a V3 of that embedding model, yes, you will have to reindex everything. There are ways around that. So for example, if I have an original domain of data, and that domain of data is good for a very specific embedding, that my embedding model fits that domain of data, and I want to extend, now all of a sudden I have a new domain of data, and I want to train a new embedding model over that, right? I have two separate, I want to combine that with my original domain of data. What I can do is I can train a new model that learns to mimic the embeddings of the old model. Yeah, I can, I have some type of L2 loss. I train a model that learns to mimic the embeddings of my old model over the old domain of data, while still providing me with useful, relevant information, relevant embeddings for my newer domain of data, right? If I just have a pure upgrade in terms of embedding model, I like one embedding model is much better than the other over very, very wide domain of data, you will have to reindex everything in your vector database. That's the unfortunate reality of it. Now, there are, there might be some tricks that we could use. So, maybe we could train some sort of some sort of encoder, or we could train some sort of multi-layer perceptron to map old embeddings to new embeddings, but I would still have to, I wouldn't be able, I would have to embed that into my vector database. Things become a little more complicated. But long story short, yeah, if you have a pure upgrade for your for your data, and you have a completely new model, you unfortunately will have to reindex a lot of data. If instead what you're looking at is maybe potentially I have a new domain of data and I want to be able to extend my old domain of data to this new domain of data as well, I can simply apply some sort of L2 loss to make sure that my old domain of data is there in line with my new domain too.
I can imagine having like optimized such a cost function and do it like that, but I'm skeptical about the performance here, because it would also mean that we are like that the new model will be using a very similar feature space. Otherwise, element of vector, like if you can use the same feature space, then it sounds feasible that it should work. But if your problem requires, or would, like, you would get significantly better performance if you can use different features, like your model will figure out what those features will represent. But I think it is, yeah, for some use cases, I think it can work, but
I totally agree with you. And that's why that's why my, that's what I'm saying. I think if you have like a new domain of data and you want, if you have all this old data that you've built an embedding model across, and all of a sudden you have this new data, and that new data is a different domain. All right, let's say your old data is all financial documents and your new data is all legal documents. And you want a new model that can handle all those documents together, then it makes sense. I think it makes sense to apply this loss to do some sort of to use the old model as a teacher, in some way, shape, and form. And if you have, the reason is because at the end of the day, these embedding spaces are not spherical. They're not spherical in these high dimensions. They're very, very anisotropic. And they, they're if we could visualize 768 dimensions, right? You can imagine we do t-SNE or UMAP, and we sort of shape them down to 3 dimensions so that we can visualize them. They're like very, very oblong, and they're very oddly shaped, and there might be like a cluster here in this embedding space, and like a different, bigger cluster here in this embedding space. They're not spherical in high dimensions. And that's why if you have a totally new domain of data, I think it's possible. I haven't actually tried, so don't take my word for it. But that's why I think it's possible to sort of have a new embedding model that handles all of your data together, not just your old data, but also your new data. If that's assuming that your data is that you have different domains. Getting pretty deep in ML here, but I imagine there is some research about this. I guarantee you there's research about this. I'm like 99.9% sure that there's research about this. I just haven't read any papers associated with it. For anybody who's listening, if you are aware of some research, feel free to reach out to me. I'd love to sort of go through some of those papers as well. But it's an open problem for sure. It's definitely an open problem.
Does Milvus support out of the box, the open source version? Does it support distributed mode?
It does. So yeah, Milvus, we have 3 different versions, and I'll start from the smallest, most lightweight to the most complex version. So the smallest version that we have is called, or the most lightweight version, I shouldn't call it the smallest version, is called Milvus Lite, Milvus Lite. And that's essentially, if you're a data scientist or you're a machine learning engineer, or you're just getting started with Milvus, that is the preferred way to go. So you can just do pip install Milvus, and then you enter your Python script in milvus.start, and then all of a sudden you have a Milvus instance up and running. Very, very quick, very, very simple, right? That's called Milvus Lite or Milvus Embedded. And then we have Milvus Standalone, which is, again, it is a service, so it is a full-fledged Milvus instance. But what it will do is it will run on just a single machine. sort of like, those old MySQL instances. It'll run on a single machine, and, you do vector search, you can put it behind a service, so on and so forth. And then we have, the granddaddy of them all, which is Milvus cluster mode. And that's where that's where things become a little bit more complicated. That's where we start having index nodes. That's when we start having query nodes, and that's when we start having data nodes to maintain a lot of that scalability and to maintain a lot of that distributed awesomeness that you get out of Milvus.
You said that sometimes you have a lot of queries at the same time, so I can imagine you can batch them to some extent. Does it make sense to use GPU here? Or because you're calculating distance, usually it is by multiplication of vectors.
It definitely makes sense to use GPU here, and GPU is good GPU is especially good for brute force search, because it's highly parallel, extremely highly parallel. So if you want, if your application, I'm a biomedical company and I'm using a vector database for pharmaceutical purposes, I really like to have exact search, and then GPUs are great. And one thing that I want to emphasize is that vector databases are not just a database, right? They really sit at the intersection of AI ML. They really sit at the intersection of, modern machine learning and data infrastructure. And they are very compute, unlike, a MongoDB or unlike a Postgres, right? They are very, very compute heavy databases. You do a lot of math in them. And a lot of this math is just tensor multiplication. This is vector multiplication, right? Computing distances between vectors. And what that entails is that kind of stuff is perfect for GPUs. And for Milvus in particular, with the release of 2.3, actually, some folks at NVIDIA actually contributed the GPU accelerated version of Milvus, the GPU acceleration portion of our indexing strategy to us. So yeah, with Milvus 2.3, you do get GPU acceleration. You do get the capability to use GPUs to build your index and to query your index as well.
Do you remember what is the boost, like the magnitude of it? I think it all depends on the type of data. Like I did my bachelor thesis, but it was 15 years ago. We've been coding algorithm on a GPU, but at the time it was it was a new thing. So I remember how fragile it is. Depends on the size. So, but expected upgrade boosts.
It's really dependent on your data. It's dependent on your GPU, and it's dependent on the type of index that you use as well. And I don't want to give any numbers. You do definitely get a boost, a pretty significant boost. I don't want to give any numbers right now because we're still doing some internal tests too. So Milvus 2.3, at the time of this recording at least, was just got released. So there are some, there's still some testing that we're doing. There's still some things that we're trying to figure out from that perspective.
Is Milvus the first vector database out there that is introducing GPU support, or is it not necessarily new?
Actually, Milvus 1 is actually the first vector database to support GPU. So Milvus 1.x. And the reason why I like to separate Milvus 1.x and Milvus 2.x is because Milvus 1.x is meant to be more standalone. It's meant to be like a standalone instance, more compact, whereas Milvus 2 is cloud native. So we use S3 as the underlying object store, and we give you the capability to expand and contract your cluster using Helm, using Kubernetes. So Milvus 1 is actually the first vector database with GPU support. Milvus 2 is not the first vector database with GPU support. It's actually its predecessor, Milvus 1.x, is what beat it to the punch, so to speak. But yeah, I would say aside from that, I'm fairly certain we are the only vector database that supports GPUs, and Milvus, and if you don't include Face as a vector database. So I consider Facebook AI similarity search to be more of a vector search library. I know a lot of folks, listening to this podcast may have used it at some point as well, and less of a database. So when it comes to a database, you want a lot of those traditional database features. You want things like caching. both horizontal and vertical scalability. And at the same time, you'll want, consistent SDKs, consistent APIs, right? So there's a lot of vector search and vector indexes. They're only just one component of a broader vector database. Without getting too far off topic here, yeah. When it comes to GPU support, I would say when it comes to GPU support for a vector database, Milvus 2, if you exclude Milvus 1, is probably the first.
What is the scale, like ballpark of amount of vectors when I will be doing I will be looking for nearest neighbor. I will need to support this operation in my system. What is the right scale to start thinking about introducing vector database to my stack? As alternatively, it is something we just discussed with Aurimas, that's you can use traditional database with user-defined function, or there are more and more plugins, extensions that would allow you to built in to traditional databases that would allow you to do this type of search. What is the right scale to introduce vector database?
Great question. I would say if you're using anything less than 1 million vectors, I would say just use a vector search library. Now, there's no one right scale to introduce a vector database per se. If you need some of the features that a vector database provides, such as filtered search, scalar search, metadata search, along with your vector search, and I can dive into that a little bit in just a moment here. If you need some of those features, or if you need an extra boost in QPS, you need an extra boost in throughput, you need lower latency, things that a database will be able to provide you that a pure vector search library won't be able to. That's when it's time to use a purpose-built vector database. I would say that the cutoff that I typically see is at about 1 million vectors. At about 1 million vectors, that's when you start getting a little bit more serious about your application. Maybe you start having to include a little bit of bits and pieces of metadata, and that's when you grow from just using a vector search library into using a proper vector database. Now, you were talking about.
I want to stop you here and double check one thing. You already mentioned latency, and it kind of resonated with me that it's quite likely is an important factor, because if were not for latency, maybe I would go with let's Spark and doing a traditional in a batch way, right? But if the latency is a requirement, low latency is a requirement, then.
But I do think that even Redis now supports a interface for ANN search, right? So probably you would not win against Redis, for example. Maybe there are other features that could be, competitive. Like you definitely will not. Would you beat Redis in latency?
Redis actually has really incredible performance, right? And we do beat Redis. We do beat Redis but that's only because we've invested a lot of time into making our vector database very high performance. I don't know how much we beat Redis by. I don't want to sort of give the wrong numbers here, but we do beat Redis. We are faster, we are faster and more performant than Redis. That's not to, that's not to throw slack on Redis. I think the performance that they have is probably better than most of the other purpose-built vector databases out there. And if you look at Redis, I think they've probably been working on this for about 2 years now, to the best of my knowledge. And the reason I think, I'm going to take a step back, and Redis, I think, has done something where they really, really build the vector search they really build vector search functionalities into Redis from the ground up. And they have the capability to build vector search directly into Redis, for lack of a better word. But if you look at, if you look at Elastic, or if you look at Postgres, or, some of these other traditional databases, traditional search engines that now support vector search, it's in some senses, it's done in a bit more of a hacky way. The architecture isn't necessarily there to support vector search from the ground up. And that's where you typically see like a pretty huge drop in performance. And that's when you typically would, while you do get the benefit of, let's say we're using Postgres, right? We're using pgvector. While you do get the benefit of being able to store table-based data, as in a relational database, you also lose performance, and you lose not performance in terms of recall necessarily, but you lose performance in terms of latency, in terms of throughput, in terms of QPS, because the Postgres architecture is not built from the ground up to support vectors. It's a little bit different for Redis. Redis, I think, has pretty solid performance. Not the best, as I mentioned, so we are a little bit more performant, but that's not to throw slack on Redis either. I think they've done a pretty tremendous. We've been working on this for close to 5 years at this point, and Redis has only been doing it for 2 or 3. Now they do have more engineering resources, but I think it's one of those things where if your application wants to treat vectors as first-class citizens, I think you should use a purpose-built vector database. Right. If your application is built around vectors, and I know we'll probably get to this a little bit later, but a lot of modern LLM, retrieval augmented generation applications, they do have vectors as first-class citizens. Embeddings are first-class citizens in these applications. So I hope that is a bit of a long-winded answer, but I hope that answers your question there.
But it definitely does. I definitely did not expect anyone to beat Redis, actually. So that's amazing to hear that it's almost it's possible, not almost possible.
Frank knows better, but I think that those indexes, and I don't know, Frank, do you beat Redis in brute force? I bet not, but I believe that you have a chance, like when we are looking for approximations.
I actually don't know if we beat Redis in brute force. And to be fair, when it comes to brute force computation, when it comes to brute force math, a lot of it comes down to the optimizations that you do at the register level. So if you have an index, there's more room to apply optimizations to boost your performance, and especially for a distributed database as well. If you're doing just brute force search, you could write a brute force vector database and probably just, brute force single instance vector database, and it's probably just like 200, 300 lines of code, of Python code, right?
Yeah, if brute force was the only only algorithm here,
it
wouldn't be so hard. Like, I'm not saying it's so easy, but
a lot of the magic of vector databases, and a lot of the secret of vector databases of vector search. I shouldn't necessarily say vector databases. Of vector search really comes from what index to use, how to build those indexes, and why should I select one index over another.
And what about combining filtering with vector search, like with looking for the nearest or approximately nearest neighbor? What are the use cases for those type of queries? And once you have such a query, do you take advantage of indexes, or you do a query and then you need to do a brute force? Maybe starting from just use cases. When would you ask vector database to filter?
When it comes to metadata, right? Oftentimes what happens is you'll have a vector field, a row, quote unquote, in your vector database. I really don't like to use that term, but or an entity in your vector database. You have a vector, and that vector is associated with maybe half a dozen or a dozen pieces of metadata. And I'll give you an example of what that might look like. If I'm doing product recommendation, okay, not product recommendation. Let me just pull back there. If I'm doing retrieval augmented generation, right? My vector corresponds to a document, right? It corresponds to a string of text, corresponds to the embedding generated through a string of text. It could be a document chunk, it could be a full document. We don't know, right? And metadata could be, let's say, the name of the document. It could be the length of the chunk in terms of, let's say, number of tokens. It could be, what are some other data? It could be the author of the document. It could be it could be the user. It could be potentially a list of users who have access to that document. right? So what the metadata allows you to do is it allows you to perform filtered search. So let's say, again, I want to find nearest neighbors or nearest documents, but I want to do it only for the larger chunks. I want to do it for this hypothetical application, very hypothetical. I want to do it only for larger documents, or I want to do it for larger document chunks. Then I could filter, I could say, okay, I want to do this vector search, but I only want to return the results where the length of the document is greater than some number of tokens n, right? Or some number of words n, or some number of characters n, whatever you want. That is filtered search. That is what we like to call, in Milvus, we like to call that hybrid search. And that is metadata or scalar filtering plus vector search. Now you were talking about, and this is why I had a bit of that pause there. I was trying to figure out, okay, what's the best place to start? From a technical perspective, if I want to implement metadata search, if I want to implement scalar filtering, I have to figure out, okay, should I apply a pre-filter or should I apply a post-filter? Or should I do this directly with the index? And that's where it starts to become a little bit tricky. Is merging metadata with the individual indexes. Now, if we look at, for example, go back to the example, Piotr, you were talking about k-means of the inverted file of IVF. It no longer works very well. And I'll tell you why. It's because I have all of these centroids, right? And all of a sudden, if my nearest neighbor vectors, I have a very, very strong filter, and my nearest neighbor vectors, I can no longer get a top 10 using, by probing, let's say, 32 centroids or 64 centroids. None of the vectors in those centroids fulfill my metadata criteria. Now, all of a sudden, I return you 0 results, right? That's a pretty bad user experience.
Distribution of data as well, right?
Yeah. You have to look at the distribution of the data as well.
No. I mean, when your database is distributed, right? It should also solve part of this problem because you can then find more, I guess, data.
You could, but typically for IVF, you use a value of nprobe, and your nprobe value is fixed. So I say, okay, I want to search the nearest 64 centroids. I want to search the nearest 128 centroids, and that value is fixed. I'll search only those. And if I have a very strong metadata filter, then all of a sudden it's like, oh, I'm doing this post filtering, and I'm returning you 0 results. That's a pretty bad, that's just not ideal. So there's a lot of details. And again, I won't go into a lot of details. I'm actually not as familiar with a lot of the details of metadata filtering, but one of the strategies for mitigating this is to maintain statistics over each metadata field. Maintain either a small index or maintain statistics over the metadata field. Now, what that tells me is this, right? If I have, I have a district, again, going back to the example of, I want to find relevant documents, but only greater than length n. I can maintain a distribution, of values. If my metadata field is an integer field, I can maintain a distribution of those integers, and I can say, okay, if n is a very small number, okay, post filtering is probably fine. But if n is a very big number, where it's a very strong filter, then maybe what I want to do is I want to do some sort of pre-filter first, and then brute force the rest of it. Right, so I'll do a pre-filter, and instead of going over the index, I'll brute force the rest of it. And what that gives me is, pre-filtering. A lot of people will say, okay, you'll do a pre-filter. Isn't that really, really inefficient? And my response to them is, it's much more efficient than doing vector search. Because what am I doing with vector search? I'm essentially doing lots and lots of math, tons of math. But if I do a pre-filter, I just need to do a comparison. Right? Maybe I do a less than, maybe I do less than, greater than, equal to, right? Just a comparison of a single field.
Do you use Elastic under the hood for it? Or
no, we don't use Elastic under the hood for this. Everything, all metadata filtering in Milvus is done just by Milvus. Is done with Milvus.
We are more lazy at Neptune. we have we have a similar, like not a vector search. It's not a use case for us, but we are experiment tracker, and that scales pretty well. Like some of the projects have millions of experiments, and each experiment has a set of parameters, metrics, and they don't need to be necessarily equal. And we need to support a search, multi-dimensional search, where you would like to find experiments that are have accuracy greater than that, where data set was that were trained on this data set, etc., etc., etc. And it was quite a challenging thing to implement based on the traditional SQL database. And we ended up doing a hybrid of SQL database with Elastic, and it works pretty well. And I was curious, how did you solve this part?
Yeah. Metadata filtering. There's a lot of tricks inside metadata filtering that even I'm unaware of, and only our performance, our core indexing team is the right team to go to for that kind of stuff.
So do I understand correctly still that you kind of need to very well understand your application to decide do you do pre-filtering or post-filtering, right? Because it's not automated for you.
We automate some of that for you. No, we definitely automate some of that for you. Actually, I take it, we automate all of it for you. And I definitely think that we have the capability to build indexes over metadata fields too. But what I was talking about earlier is just sort of giving a sense as to why metadata search is hard, and why you would want to build metadata search in the way, why it's harder to do metadata search than most people think, is because you have all these different things that you have to think about, all these different things that you need to take care of. And it's not as simple as just saying, hey, I'm going to do a post filter, or I'm going to do a pre-filter. It's not that simple, right? You have a lot more things that you have to think about, and a lot more things you have to take care of. And in some situations, you'll do just a pre-filter. In some situations, you'll do just a post filter. And in others, you'll combine the two. You'll do both pre and post filtering. And which sort of strategy you do depends on the distribution of your data, not your vector data, but of your metadata, of your scalar fields, but also, let's say, how much data that you have. Right? If you don't have that much data, it's better just to apply a pre-filter pretty much all the time.
I think it balance those two strategies, pre-filtering and post-filtering. I see a proper kind of a property, statistical property. Of course, it can be, I'm saying that approximately it should work. I see edge cases as well, but like, what is wrong with pre-filtering? The wrong thing about pre-filtering is that potentially you will need to do a brute force over a lot of vectors, right? So then it is maybe better to go to post-filtering. But if the amount, like the filters you applied, still the subset is pretty big, quite likely post-filtering is not so terrible, because those points are not so unique. Of course, there are edge cases, but I think that in real life cases, it helps. This dependency helps. So for some use cases, it's better to use this. For others, it's better to use the second option.
Absolutely. Yeah, I agree with you there. I agree with you. And again, it's also dependent on the type of vector index that you use as well. So if you use a graph-based vector index, it's easier to do quote unquote, well, it's easier to do combined filtering. I'm not going to call it pre-filtering, I'm not going to call it post-filtering, but it's easier to traverse the graph and to continue traversing the graph until I let's say get a set of fields that are there for my metadata fields. Again, or I get a set of vectors that fulfill my metadata. And again, it's not that simple. If I'm doing some very, very, very strong filtering, it's probably better just to apply a pre-filter, get an index, get a reverse index to the vectors, and do a brute force over those vectors, right? So it's tricky. it's tricky, and there's no one great way to do it. But I just want to give an idea as to why it's hard. But you're right, Fyodor. It's under different circumstances, you might want to do a pre-filter and you might want to do a post-filter, and it really depends on what you're trying to build.
Let's say, let's take a RAG example, right? So retrieval augmented generation. Sometimes it does make sense to do ANN search, but sometimes a user query might be just a keyword, right? And then probably keyword search is a better thing to do. Are these kind of combined queries possible in Milvus? Like, can you do both vector search, ANN and keyword search query, like at the same, not necessarily at the same time, but yeah.
Retrieval augmented generation, new school use for vector databases is to just use it in combination with documents, to use it in combination with large language models. And what you'll do is you'll match prompts with those documents or with those document chunks. So basically, vector databases, long story short, are used as a way to inject domain knowledge or domain data into your large language model. And I would say, if we're talking retrieval augmented generation, yeah, there's a lot of different ways to do it, but the vast majority of RAG or RAG apps use vector databases as the underlying data store. Now, going back to your question, Armas, which is, can I do in Milvus, can I do that traditional keyword-based text search plus vector search? And the answer is you can't. But there's a very, very specific reason for that. And we're looking at potentially adding that to Milvus as well, which is because we want Milvus not to be specifically there for text only. Right? Later on we may want to add this feature. I'm not going to rule it out completely, but we want vectors to be the first class citizens in a vector database, and at the same time we want to give you the capability to eventually do retrieval augmented generation, for example, across other forms of data as well, across images, maybe video, right? You can imagine eventually I might want to input not just the relevant documents into my large language model, but also relevant images into those large language model, maybe relevant audio snippets in that large language model. And if I tie a vector database very closely with traditional keyword search or traditional text search, I lose that capability. I lose the capability to go multimodal, right? Now, that doesn't mean that we won't add that feature into Milvus later, but we are cautious. I think we're a little bit more cautious than other vector databases. And the reason is because, yes, while keyword search is very, very, it's very, very useful in many cases, we want to be agnostic. We want to be more agnostic to the very specific type of data that you decide to store. It could be text, sure, but we also want you to be able to store, let's say, IMU data, molecular structures, right? Maybe some time series data or some geospatial data in your vector database. But yeah, that was a sort of a quick, like a 1-minute intro into retrieval augmented generation. Just scratch the surface of that, and also hopefully a bit of insight as to why we decided to build Milvus the way that we did.
But I think users usually still store text chunks as metadata, right? It's not like text is not stored.
Yeah, you can. I actually encourage users to store the text chunks in some type of object store. So rather than using metadata fields, rather than storing it along with the vectors as metadata fields, you simply build a reverse index, or you store it in some sort of key value. You store your text chunks, your document chunks in some sort of key value store, or you store it as just raw bytes in let's say S3. And what that gives you, and as long as you maintain an index, so you can store, let's say, the URL, you store the location to that document or to that document chunk as a part of the metadata, right? So that averts the need, that gives you much more efficient storage, and that averts the need to store the entire document chunk or the entire document, the text of the document, as a metadata field as well. Now, do we have users who do that? Yeah, absolutely. And you can do that, right? You can do that. There's nothing wrong with that at all. But that's for me, that's my general recommendation, is to use the vector database for, really hardcore down-to-earth vector search, and to just in the interest of storage and just in the interest of sort of efficiency, you can retrieve those chunks using the entity IDs or using the ID field in Milvus. So you just maintain a reverse index to the original document or document chunk.
Putting scale aside, okay, we have a vector, we have a Neptune documentation, and we want to write a chatbot that would be helping our users use Neptune. We of course, Neptune is we of course can use, let's say, ChatGPT, but ChatGPT is not so well trained on our documentation or code base. How to connect it? You said that vector database can be used to kind of ingest knowledge to a model. What is a typical setup here?
We actually, if you want to see an example of exactly what you're talking about, Peter, in action, we have an application called OSS Chat. So it's OSSCHAT.io. And if you go to that website, you can actually see there's a lot of what we've done is we've indexed a lot of documentation for open source projects, both from the website as well as from GitHub. And you can ask and answer questions about the documentation. One of the first ones that we index is Milvus. And what ends up happening is if you ask ChatGPT or you ask GPT 3.5 or even GPT-4, how do I perform a query in Milvus? It actually gives you the wrong answer. It'll like hallucinate an answer for you. And if you ask OSS Chat, it gives you the right answer because what's going on is, I'll prompt it, how do I query in Milvus? And that prompt will get turned into an embedding. And all of my documents are also embedded into the same space. All of my open source documentation is embedded in the same space. And it will find the most relevant pieces of open source documentation. My vector database it'll return that. At the application level, I'll return those documents along with the original prompt. And now what I have the capability of doing is with a bit of in-context learning, with a bit of prompt engineering, I can ask the LLM to focus on the results that I've returned from my vector database and use those results to answer the original prompt. Use those results to.
Would you say that it is kind of like, in theory, we could put into the prompt all those document pages, but of course we can't because prompts cannot be so lengthy and it would take forever. With vector search, with vector database, you can quickly figure out what are the most relevant pieces of information.
And by the way, this is called retrieval augmented generation. This is exactly that, right?
Yeah, this is exactly retrieval augmented generation. This is exactly retrieval augmented generation. And we built an example application to demonstrate that and to demonstrate what that potentially could look like as well. There are many forms of RAG, I want to be very clear, but the most common form of RAG, of retrieval augmented generation, utilizes vector databases or utilizes vector databases in conjunction with other data stores. So, you can have these tree-based indexing. You could potentially use a graph database as a part of RAG, but vector databases are most commonly used. And the reason is, again, going back to the semantic properties of these embeddings, going back to the idea that, I have this prompt and I want to match the intent behind the prompt with the right documents. And what is so awesome about RAG is with vector databases is as my embedding models, as the models that I use to embed the prompts and the documents together into the same space, as those become better, my RAG application is I just snap my finger. I don't have to do anything, and my RAG application is going to become better as well, right? As my prompts become better, so is my RAG application. So really, I can improve all of this without writing a single line of code. I just improve the models and I improve the prompt engineering behind all of this, right? I have a better understanding of how these underlying large language models and embedding models work. But no, you're exactly right. This is exactly retrieval augmented generation. This is exactly RAG, and it's the most common way to do it today is definitely with a vector database. I'm happy to chat a little bit more about anything as well. But one thing I do want to say for the audience out there that's listening is, definitely go play around with Milvus. And if you're a solo developer, I'd recommend using Milvus Lite. So if you do Python, just pip install Milvus. It's an easy way to get started with it. We have documentation on milvus.io. Feel free to reach out to me as well if you have any questions, comments, concerns.
Where we can find you?
Oh yeah, you can find me on LinkedIn. If you just search Frank Lou Zillis, you should be able to find me on LinkedIn. You can also find me on Twitter. I am not as active more recently as I have been usually, but you can find me on Twitter as well. I also have a personal website as well, with some blogs on there if folks want to go read it. But yeah, I talk about everything from vector indexes to I have a newer one coming up on sort of how sort of analyzing how good transformers are really for computer vision, and really comparing transformers, comparing self-attention versus traditional pure convolutional networks. So a little bit of everything on there, right? And always happy to chat with anybody about Milvus or about any of their open source projects that we maintain. I also encourage everybody, I mentioned this a little bit in the podcast as well, to go to osschat.io. It's an example of retrieval augmented generation that we've built at Zilliz. Again, that's osschat.io. You can chat with open source projects there. And yeah, always happy to chat more about Milvus. Always happy to take any questions, any comments, any concerns from the audience and from the two of you as well.
Thank you, Frank. It was a super nice conversation. And of course, thank you to everyone who was listening. And I really hope to see you in the next one.
The ML Platform Podcast was brought to you by Neptune AI. If you would like to learn more about ML platforms and ML ops, check our blog at neptune.ai/blog. Follow us on LinkedIn or subscribe to our YouTube channel. Also check out how we help teams solve ML ops challenges with our experiment tracking at neptune.ai. To get notified of future episodes, follow us wherever you get your podcasts. Thanks for listening and see you next time.